Okay, this is a quick introduction to Xfoil and a little bit of the science and underlying algorithms behind it. Now, first as a reminder, so what we're talking about primarily is the prediction of 2D aerodynamic parameters over an airfoil profile. And so when we talk about lift coefficient, drag coefficient, and moment coefficient as measured by Xfoil, we're talking about the 2D versions of lift, drag, and moment coefficient. Now you can relate those directly back to the 3D versions, which is classically how we define lift, drag, and moment coefficient with the equations below, just by taking lift and dividing that by span. So we're really talking about lift per unit span, drag per unit span, and moment per unit span. Notice that if you take a rectangular airfoil, the wing area S is the span B times the chord C. So those two are simply related if you take that two-dimensional airfoil and extend it outwards in a three-dimensional section. So now regardless, when we're doing this with Xfoil and we're calculating these two-dimensional coefficients, we'll learn how to correct those later for three-dimensional wings. Now, as we'll see in Xfoil, it's really only good for airfoils. It's designed to be able to calculate these parameters over a streamlined shape. And that's very important. So when we talk about a traditional airfoil shape where we have that rounded leading edge and that faired trailing edge in the back, in order to give us a compromise between good lift, high lift, and good drag, meaning low drag, then those are the types of cross sections and profiles that Xfoil and other panel methods are really designed to be able to study. Now, if we're just looking at the potential section of that, it's okay if we look at non-streamlined bodies, but when we throw on the viscous part, which is really that piece that we want to be able to utilize Xfoil and other panel methods for, that's when we can really only use it for streamlined shapes. Doesn't work so well when we start talking about separation behind bluff bodies or non-streamlined bodies or at high angles of attack. Now, what we want this method to be able to predict is that behavior of the lift, the drag, and the moment, or the non-dimensionalized values of those two forces and one moment about the angle of attack. So just to remind ourselves what this looks like is a typical lift curve slope is going to look something like this, where we have a linear section that starts off at that zero lift angle of attack and continues in a more or less straight line until we reach this region of separation where that lift starts to drop off. So we have this starting point, and then that zero lift angle of attack, that linear increase at low angles of attack, and then finally we have that nonlinear stall region. So defined by that stall angle of attack. Given these parameters, this pretty much is all we need to be able to describe what that lift curve slope looks like. Now, drag is typically a little more complicated, and this is just a notional value of what drag might look like. That drag is going to be very highly dependent upon the shape of the airfoil and the Reynolds number regime that you're operating in. So we will generally have some region which is fairly flat, and then once we start to get into those higher angles of attack, particularly when we're around that stall region, then we will see that drag increase very, very quickly. And then finally we have our drag divergence portion here, where we have that large increase in the drag, which is also going to give us a nonlinear region for our moment coefficient. Now, depending upon where you calculate that moment about, you're typically going to have a fairly constant region of moment coefficient up until you get to that stall angle of attack, where that drag starts to diverge and really changes the distribution of forces over your airfoil section. Now, our forces on the airfoil, again, are calculated by our pressure forces. So we have this pressure distribution. Now, ultimately, any method we want to use, we want to be able to calculate this pressure field, which is given, of course, by the velocity field. Again, we can relate that local pressure over the surface of the airfoil simply by going back to our Bernoulli relationship, where we have pressure related to 1/2 rho v squared. So calculating that pressure force is really determined by the velocity first, calculating the local velocity vector around the airfoil, and then calculating the pressure directly from that, and then calculating that pressure coefficient, which is the local pressure at a given location of chordwise location along that airfoil, and then we integrate that along the upper and the lower surface, and that will give us our lift coefficient. Now, when we're calculating the Inviscid value of our airfoil parameters, we'll get a lift coefficient which is based upon this pressure field, and we can also get a pressure drag coefficient. It's very important to note that even though that lift coefficient will typically be pretty close to what that viscous lift coefficient is going to be, that drag coefficient will not, because it's really our viscous forces that are going to be dominating the value of our drag in most scenarios. So here's an example of what that pressure field might look like, and these are both GWiz graphics coming out of Xfoil. So you can see for this particular NACA 0012 airfoil, which is symmetric, at that 0 angle of attack, which also in this case corresponds to the 0 lift angle of attack, we see a speed up over the top of the airfoil. We have a maximum pressure location located somewhere, about the quarter chord location, and then that quickly drops off as you proceed towards the trailing edge of the airfoil. Notice that you do have a stagnation region near the leading edge, so you actually have a little bit of a pressure increase there. Now, as you increase that angle of attack, looking at the bottom, you can see that at first the pressure distribution changes. Your suction pressure that you have on the top is much larger than the suction pressure that you have on the bottom. That stagnation point shifts a little bit to the lower side rather than being directly at that leading edge point. And also that maximum location of negative pressure moves closer to the front of the airfoil. When I say negative pressure, we have to be careful about that. We're not actually talking about a negative pressure force itself. This is in relationship to the ambient pressure. So this pressure is a suction force lower than our static pressure value that we have upstream of the airfoil. Now, during the early days of fluid mechanics, when they were trying to equate the Eulerian or Euler equations of motion with flow about an airfoil, they hadn't thrown viscosity into the mix yet, so they didn't have a really good understanding of how viscous forces were affecting the flow about bodies, particularly about lifting bodies. And so this resulted in something called D'Alembert's paradox. Since there was no viscosity, there was no drag, and there was also no lift. So when you were solving these Inviscid equations of motion in a two-dimensional flow field, you'd calculate the flow about the body, and it would look nothing like you would expect to see in real life. Now, what actually related this back to what we see in the real world is this condition called the Cuddy condition, where you take a circulation about the airfoil rather than having a purely irrotational flow. You're providing this circulation of strength gamma and then forcing your streamlines to essentially attach such that you have a bounding streamline leaving the trailing edge. Now this condition, even though it's still inviscid, provides you with that realistic solution that you would see in a viscous flow. Now, this was initially really discovered by Prandtl, and this little picture here of Prandtl's actually shows the same type of experiment that he was running, taking an airfoil, running it through a flow, in this case seeded with little particles so you could trace stuff out along the surface, and showing that when you get a starting vortex, when you start moving that airfoil, and using Kelvin circulation theorem, where the time rate of change of your total circulation of the flow is going to be equal to 0, it means that you have to have a bound vortex attached to that airfoil. Now, we know this is true because when we stop that airfoil from moving, we also see an opposite sign vortex from the starting vortex shed, and so those two vortices essentially cancel each other out. So we have that bound vortex, which is providing this rotational flow about the airfoil. And so this really relates what we have with that flow with no circulation, where if we solve those Inviscid irrotational equations using the Laplace's equation, we'll get this unrealistic solution. But if we add, by superposition, this circulatory flow on top of it, where we have this rotational flow moving around the airfoil, add those two together, then we get this realistic flow with the circulation, and then now we have this nicely attached flow moving around our airfoil, even without viscosity. So we can put all these things together, and this really becomes the foundation for the circulation theory of lift, where we have this inviscid flow, which is not creating any force. We get neither lift, no drag generated from the airfoil. But if we relate that lift with the circulation through the Joukowsky theorem, and then use the Cuddy condition to make sure that those streamlines leave at that trailing edge of the airflow, then we get lift acting on our airfoil, which is directly proportional to the amount of circulation that is generated. Now, there are lots of nice videos that can actually demonstrate this phenomena. I think the best example is really to go back and look at some of the original stuff that Prandtl did, and so you can kind of see this relationship in the simple experiments that he ran, where you're taking this airfoil, you can see that starting vortex being formed, and then you have that circulatory flow around the airfoil. And you can actually see this if you look at the particles moving around the airfoil. You see things are faster over the top and relatively slower over the bottom. And again, that is, if we could put ourselves in the frame of reference of the airfoil, it would actually see this rotational or this circulatory motion around the airfoil, and that is that circulation value gamma. Now we can go ahead a little farther here to see where we actually have that stopping vortex, and notice when you start you get the starting vortex, when you stop you get that shed vortex, which is that bound circulation coming off of the airfoil. And you can see that those two vortices are both equal and opposite to one another. Again, demonstrating Kelvin circulation theorem, that we start off with zero circulation, we actually end up with zero circulation, net circulation as well. So that d gamma dt is equal to 0 throughout the entire motion of this airfoil, before it's impulsively moved, during the impulsive motion, and then after the impulsive motion as well. So this really allows us to kind of relate what we have in an inviscid airfoil to these viscous solutions. So as we'll see, the way that we're solving this flow is still really starting off with this inviscid approach, where we're ending up with these unrealistic solutions, and then we're forcing the trailing edge to meet at the leading we're forcing the flow to leave the airfoil at the trailing edge, and that takes all these different possible solutions that we have down to one single realistic solution. Now, we'll note here another example. What you can see is the flow actually traveling over the airfoil, which again is demonstrating this this circulation, and it's really this this unequal motion. So if we take these streamlines moving over the airfoil, which you'll notice they're starting off all at the same location, as they're moving over the airfoil, that circulation moving around, in this case in a clockwise fashion, is moving the flow over the top of the airfoil faster than the flow over the bottom of the airfoil. And then you end up having these two sections leave at different times at that trailing edge location. And we'll come back and look at this video later when we look at other cases at higher angles of attack. Now, when we look at Xfoil, it's really what's called a vortex panel method. And we're not going to go through this in detail yet. We'll come back later and look at this in a more rigorous approach. But what we're doing is essentially taking that airfoil, breaking it up into individual panels, and replacing each panel with a vortex of arbitrary strength. So we're going to use a small gamma for each one of those. And then we essentially change the value of those gammas until we're able to meet that kata condition. Sum all those gammas up, and that gives us the total circulation or lift for the airfoil. And then once we have the value of each one of those gammas, that's going to tell us what the local velocity is over that particular airfoil. Now, in reality, it's a lot more complicated than this, but this gives you the gist of the idea that Prandtl came up with, and he was able to develop some other methodologies around this concept that we'll go into more detail later. Now, what's this got to do with Xfoil? This is using that basic approach, which is an Inviscid panel method, breaking that airfoil up into lots of small vortices, and then adding boundary layer corrections on top of that. So every time you're running Xfoil, even if you're running it in a viscous mode, it's running an Inviscid solution first and then putting viscous corrections on top of that. Okay, this is a very useful tool, and although we'll look at other applications and different formulations of panel methods throughout the semester, I always recommend that this is a very robust code. You have access to the source code, so it's one of those things that you can implement in lots of different fashions. So it will always be the one that we kind of go back to first. Now, of course, no tool is very useful unless it actually works. So here's a comparison. So this is data from Abbott and von Duenhoff for a NACA 4412 at a Reynolds number of 3 million. So you can see the data for both the lift curve slope, the moment coefficient, and then finally your drag polar. Notice that there are some areas where it agrees really well, and then some areas where it does not, mostly in those nonlinear regimes where viscous effects start to really dominate, primarily around those stall angles of attack. Here's another example. This is an LA203A. It was a Douglas low moment coefficient airfoil. So this comes from the Douglas Aircraft Company. You can see comparisons in the OSU tunnel with the original data from Liebeck and Camacho's tests, also compared with Xfoil. Again, you can see generally it has very good agreement throughout the low angle attack region up until you get to those stall angles of attack. So there are limitations to this. Note that it does predict the stall point pretty well. You can go back and look at those previous plots that we showed, but not really the values of the coefficients beyond. That's because inherently stall is a three-dimensional phenomenon once you actually have incipient stall set in. So, once you get into this turbulent regime, all bets are off. Also note that it doesn't work really well at very high Reynolds number. This is due to the fact that the Xfoil code is using a dimensionless Navier-Stokes equation, which has a 1 over Reynolds number factor in front of the viscous term. Generally what you can do is use a high value of Reynolds number since it becomes very asymptotic in behavior at those high Reynolds numbers, and that's usually fairly consistent with what you'll see in most high Reynolds number applications. But keep in mind, Xfoil was primarily written to be a low Reynolds number airfoil solver, and that's really where its strength lies. You also need a clean airfoil. Rough or irregular airfoils will not converge to a solution. If you do end up with some funny shapes, you can come in and work with the panels, which we'll go over later, and sometimes you might be able to converge to a solution. The common Xfoil version also only allows simple flaps. Other high lift devices, such as multi-element flaps, will not work. You need other codes such as ISIS or INSIS to be able to actually implement those. Now, the basic Xfoil menu structure is pretty simple. You start off with a main menu, which allows you to define your airfoil geometry, and then travel to all the other menus. Most of the time, you'll spend your time in the operations menu, where you'll actually develop your lift curve slopes and your drag pullers. You can also go to the geometry menu or the airfoil paneling menu when needed to be able to change some of those parameters, and we'll explore a little bit of that as well. All right, let's take a look at Xfoil and see what we can do with it. Okay, let's go ahead and start up Xfoil. As you note, when you start up, it's a terminal or command line driven program. So you'll run all your commands directly from one of these menus. The period in front of one of the commands will take you to a lower menu, and hitting return with no command will take you to the upper menu. So in this case, the only menus that we'll be really interested in for now are the operations menu and the geometry menus. We'll come back and look at some of the others later. So let's start off with looking at a very simple NACA airfoil. So we'll do a NACA 0012. It'll tell us how many panels it's using. Notice that it's using 160. So in the previous slides, we had a fairly limited number of panels when this was initially developed. Again, you were mostly solving this by hand. So it wasn't until the 50s and the 60s where you had computers when you could actually program this in and solve lots of points relatively quickly. So we'll go to the operations menu, type OPER to get us to the operations menu. Now, when you first start Xfoil up, it shows you what the menu commands are. When you go to other menus, you will not see that unless you type a question mark, and then it will show you all of the command options. It's a good idea just to come in and play around with this. You can't break anything on it, so you might as well just see what happens. Now, the basic menu commands that you're going to start off with are alpha, which allows you to look at a single angle of attack. So in this case, we'll start off with 0. Go here and resize this window. So we'll do an alpha of 0, and then it tells us or shows us what we have here for our airfoil angle attack of 0. It's a symmetric airfoil, so we're going to have a lift coefficient of 0. Notice it's also calculating our moment coefficient as well as a value of our pressure drag. And notice in this case it's negative, so we're actually getting a little bit of a suction force due to that stagnation pressure value up here near the leading edge. So now if we do an angle attack of 5, we can now see a difference in the pressure between the upper surface, where we have this negative value of CP, or the suction pressure, and then we have a positive value of CP down at the bottom. And that's really about it, right? So that's pretty straightforward. Now, if we want to run a range of angles of attack, we can use a sequence, or alpha sequence. In this case, I'll run from 0 to 12 in increments of 1, and you can see it solves all these values for us very, very quickly, right? So a sweep of alpha ranges, a range of lift coefficients, and moment coefficients. Now, it's really only useful to us from a practical standpoint if we're calculating viscous effects. So to do this, first off, we want to be able to turn viscosity on. And when we do that, type in VISC. The first thing it's going to do is ask for a Reynolds number. So you can't have a defined viscosity in this case unless you actually have a value of Reynolds number. So I mentioned we're going to typically be operating in relatively low Reynolds number ranges, so I'm going to put in a value of 500,000. Also notice we have an option of setting a Mach number. In this case, we're only going to look at incompressible effects. We'll come back and look at Mach effects later. So now I can rerun this. I'll do this for the angle of attack of 5 again, and now you can see a comparison between the Inviscid solution, which is shown in the dashed lines, as well as the viscous solution. So you'll notice the blue for the suction surface and the red for the pressure surface, as well as the boundary layer here shown between the difference between that upper and lower surfaces. And it's a slight difference or separation away from the actual surface from the airfoil, and then our actual viscous wake here in the back. Now in this case we do have a Reynolds number, an alpha number, angle of attack, lift coefficient, moment coefficient, and now a drag coefficient that's composed of both of our pressure and predominant viscous drag forces, and it calculates a lift to drag ratio for us. Okay. Don't worry about this in critical number right now. We'll come back and talk about that later. Now likewise, we can also run a sequence of angles of attack. So we'll run the same range that we ran before, and it calculates all these for us. Now, you'll note here there are a couple of cases where it didn't do so hot. In this case, keep in mind what it's doing is running through these and trying to converge to a solution with these boundary layer corrections that are on top of it. And so it actually takes a lot of iterations. Sometimes it doesn't always converge. Since Xfoil was written quite a while ago, so the number of iterations is still relatively at a low value. So I recommend turning this up to at least 100. So now if you rerun this, you'll actually see that it performs a little bit better. So maybe you want to go back and rerun some of these as well. But keep in mind what's happening at these higher angles of attack. The airfoil is starting to stall, and that's where Xfoil begins to break down and will not perform as well at these high angles of attack. Now the final thing we want to be able to demonstrate is actually plotting a polar. So to do this, we go back to our operations menu, look at all the commands that we have, and so we want to look into these commands that start with the letter P. These are all of our polar commands. Primarily toggle the polar accumulation on and off, and then actually plot the polars. So the first thing I'm going to do is turn PACC on, and so now I have a polar. And in this case, if you want to save the polar file and then reload it later, you can write this as a save file, name this whatever you want to. I'll call it save polar, and then you also have a dump file where it dumps this to a text file. I'll call this dump polar. Of course, you can name these whatever you want to. Now when you run this, it's actually going to store these values. So I'm going to rerun the same values again, a sequence from 0 to 12 at increments of 1. It'll calculate this for me, but now I can run a polar plot, and it plots not only the lift curve slope for me, as well as a moment coefficient, and then my transition locations. This is where our airfoil is transitioning from laminar to turbulent flow. More importantly, it plots our drag polar for us. Now the real value in here is you want to use this for airfoil comparison and then airfoil design. So you want to be able to compare multiple airfoils with one another. So to do that, you're going to turn the polar accumulation off. We're going to change something on our airfoil. Let's say in this case we want to just change the Reynolds number. So I'm going to change the Reynolds number, change it to 250,000, and then I'm going to turn my polar back on, and then I'm going to rerun this. In this case, I'm not going to save these values. I'm not worried about reloading them or looking at them in a different program, so I'm just going to leave both of those blank. I'm going to rerun this sequence again across the same ranges of values, and then plot this again. And now notice I have two airfoils, or two solutions on here. One for the NACA 0012 at 500,000 Reynolds number, and the other for the NACA 0012 at 250,000 Reynolds number. What you will note is our lift curve slope look pretty close to one another. Our moment coefficients do change, so there is a substantial change in both of those. So a change in that Reynolds number does have a pretty big impact on the moment coefficient. Predominantly, you'll notice that the drag polar is very different. Our zero lift drag is much higher than the case for 500,000 Reynolds number. So there's a pretty big impact in the overall behavior of this airfoil as shown by that drag polar. Now, we can do this with lots of other examples. Let's keep our Reynolds number the same. Turn our polar accumulation off, go up one menu, and let's put in a different airfoil, something that has a little bit of camber to it. Go back to our operations menu, turn that polar accumulation on, and then run through that sequence of angles of attack again. Now in this case, I'm going to start off at -2. I'll go to 12 still in increments of 1. I'm starting off at a lower angle of attack because now that I have an airfoil with camber, that zero lift angle of attack is going to be shifted on my lift curve off to the left. Okay, rerun it again, and now I can plot my polars. And here now I have three curves. I have my two NACA 0012s, and then I have my NACA 4412 right here with this new lift curve slope. And you can notice what's happened on my drag polar. It's actually shifted up pretty high, since now I have this camber value at the same angle of attack, say alpha of 2 here, where my lift coefficient is relatively low, about 0.25 for my two 0012s. It's actually relatively high, about 0.7 for my 4412. And in this case, I can go through and compare lots of other airfoils. I can turn my polar off again, go back one menu, and let's say, hey, let's try something that has a little bit more thickness associated with it. Go back to the operations menu and rerun this all over again. Right, and now I have a whole nother airfoil on here. You'll notice the thickness doesn't really change the lift coefficient that much. It does change our separation behavior up here at the stall angle of attack, but it does have a larger impact on our drag polar. You can see that's exhibited here by a slight increase in drag as we've gotten a little bit thicker, but we also end up having a higher lift coefficient at the same value of drag coefficient. So these subtle changes can have a pretty big impact on how your airfoil is going to behave, which allows you to go through basically lots of different airfoils to try to find one that's going to be optimum for your particular design case. Now this was an initial introduction. We'll come back and look at some more details later, but this is enough to get us started. All right.